certainly seems a long time since as a young apprentice I got sent for stripe paint. Whereupon when I got to the stores, he said, "We have no stripe paint, mate, but we have got half a brush." He said, "Which half do you want, the back half or the front half? Go and ask him." Anyway, that was my introduction to life as a steelwork contractor. We're not here to talk about that. As the title suggests, it's really to try and look forward, to look at the future of tall buildings. And in doing so, every corner I looked in and every person I seemed to speak to, there was an underlying theme. And that was literally, where in the world are we going to build by 2050 and in the future? And secondly, how will technology assist us? Between those two things is actually what you build, straddling technology and geography. So it seemed quite a natural place to start to look where the world economy was going, because there's a very direct correlation between where tall buildings are built and the economic activity of the area. Certainly up to now, North America, Europe, Asia, and I include China as a mature economy in this, has been where most of the activity is. What I would suggest is that we'll see a drift. We'll see a drift to South America, we'll see a drift to India, Indonesia, and Australasia, the so-called southern economies. And as a result of that, what previously were the defining features of tall buildings, that is to say, in certain areas, the wind almost governed most of the time, and strength, stiffness were the defining criteria. I would suggest as we move further south that at about 40 stories that seismic activity will define what it is that we build and how we build it and the priorities. And also from a sustainability standpoint, that the temperatures will change. So the long-standing American template would have to be questioned, I would suggest, because it doesn't transfer easily into those climates and geographies. And when you actually look at the number of variables, the template that you've got to work with, they're actually quite limited. And the real skill is how you put this limited palette of technology together. Facades and elevators and sustainability certainly travel internationally, but the foundation structures and some of the fire escape strategies and materials are definitely locally based. So the way that you put those things together, and I loosely term how as being technology and where being geography, in many ways defines what it is that you will build. And you can extend this beyond tall buildings, I would suggest. So what I would like to do is, by reviewing 2 or 3 jobs that we've either completed or are under design, to describe a little bit how they work and the influence of the geography and the climate, amongst other things, how those have influenced what it is that we build, and the effect that local technology has had. What you see there are the conceptual models for Renzo Piano's landmark tower in Seoul. It was 620 meters high, very susceptible to aerodynamics, and the top of the building was very important. By sculpting the top of the building, you could halve the forces, effectively the overturning moment that you got at the base. So we studied a whole plethora of shapes. It was really the big brother of the shard. So the way that we organised the core was critical to the net to gross. So in a holistic sense, what we first did was to decide on an elevator strategy, strangely enough, and the structure would follow. We stacked elevators, we used sky lobbies, and altogether we achieved a core. The area of the core dedicated to elevators was 1/2 of the core that we used at Canada Square in Canary Wharf. And that was for a population of 14,000 people on a building of 620 metres. A very significant move. We then made sure that the facade worked. The facade being probably the biggest influence on the energy consumption and the demand on the HVAC systems. We wanted to maintain daylight, so we had an adaptive facade. But basically, when the sun wasn't shining on the facade, it exposed the interior to daylight. We used a ventilated facade, and we gave the facade a high thermal performance. So the two key drivers to start with were the elevators and the facades, a recurring theme, I would suggest. The next major step forward was, for those of you that have either worked on or understood tall buildings, the next natural thing to reach for was an outrigger scheme, which is basically the ski poles that you would hold on to stabilize yourself when skiing. The outriggers form exactly the same solution. They are the arms. And you can see here the intense stress concentrations that occur at the outrigger positions. We chose to question that, and we chose to question it for two reasons. One, the outriggers can drive the size of the core. We didn't want that to be the case. We wanted to smooth out the stress concentrations over the whole area. And essentially what we created was, on the outer skin, a double helix. That double helix connected into the floors, and it shared the forces, stability forces, between the core and the external skin. What that meant was that every single piece of the building was contributing in all cases: wind, seismic, and vertical. There was no wastage there. And when we put the three major elements together, we created what we believe is a unique concept, because we get a relatively uninterrupted facade, we get a minimized core, and we get every single piece of the structure contributing. That helps in damping. That was really a stiffness, wind-driven structure. And 15 years before, we were working in Tokyo with Renzo Piano again on the Hermes Tower. And we had a very, very small site, 10 meters by 50 meters, probably the most expensive site in the world, some would say. We needed to maximize the net to gross for that. And we visited indigenous technology. We looked at the pagoda, because there was a history of this type of structure surviving under severe earthquakes. And it does that because one of the columns lifts, as you can see on the diagram on the right. And in lifting, it reduces its stiffness and therefore limits the amount of energy drawn out of the earthquake event into the structure. So we thought that was rather a good idea, because if we could limit the amount of force or energy that we absorb from the ground, then we could minimize the element sizes and increase the net to gross and the land usage effective to this very expensive site. So we decided we would adopt a stepping column. And on the sketch on the left, we severed the column so that in an earthquake it lifted. And the real point of this story is that we effectively halved the overturning moment that the building experienced in an earthquake. That meant that the front column on that building was only 6 inches in diameter. The back column was 1 meter 20 square. So it was effectively an outrigger scheme. But it enabled Piano and his team to really liberate the space in the building. And behind both of those jobs, in essence, was the spirit of collaboration. And when we moved to Mexico, we wanted to take the knowledge that we gained in Tokyo and test if there was opportunity to extend this thinking in some way. And there was, because as well as having a benign climate, which set an agenda for the building in Mexico, incidentally a Richard Rogers Sturck Harbour design, with Arup, we had very soft ground. And when we tried to explain this to people, it's quite difficult. So we built a model. Will Algard made the jelly. I made the piece of wood and things, and Tom Wilcock filmed. Don't know if they're here. So effectively what you see is I'm rocking the table ever so slightly. That small movement is being amplified through the jelly, and the frequency of the jelly and the frequency of the mass on top are such that you get an amplified, or you get resonance basically. And what's really happening in Mexico City is that the earthquake comes through the rock, it then meets a soft bowl of material. That activity is amplified and is very close to the frequency of the building above, and that's quite dangerous. Added to that, perhaps the biggest influence on the design of the building was the lack of infrastructure, a recurring theme. We needed to find space for 2,800 cars on this site, compressed in a city site. So what we did, we created a basement of 7 stories to the influence of earthquakes, and thirdly, the lack of infrastructure, which forced us into a certain design direction. Because the climate was so benign, we had the opportunity to really think through the facade, and what we chose to do was put a veil down the outside of the building, which really shaded us from direct sunlight, but gave access to the outside, and each of the 4 sides of the building were different, ever so slightly different. They were different because the angle of the sun was different. We looked at explored opening windows, which is kind of at its limit at 50 stories, rejected it. We had very poor fresh air, I would say, smog in Mexico. And we had very high sun angles, which meant that the shading of low-angle sun was absolutely significant. But the major difference, and part of the reason for discussing this project, was that it's a totally antithesis of what we did in Seoul. And the reason is we wanted a light ductile building, and we achieved that with a very competitive steel weight of less than 150 kgs a square metre, which those of you who've been involved in tall buildings will recognise as being very competitive in terms of steel quantity. We avoided a core. A core can weigh anywhere between 20 and 50,000 tonnes, and when you have to support that on poor ground, it really is an issue. To avoid that is a real benefit, because once you set that core moving, you build up huge stresses, huge forces inside the building, so there's a real advantage in a ductile frame. You can see here just some of the mock-ups of the facade. It's a deep facade, and it sat in front of the ductile frame, giving access for cleaning and certainly shading. And one last thing is it was hung over 3 stories, rather like this, so that the complex facade could move with the earthquake in an extreme event without damage. But the real key to the job was, in the same way that we developed the damper in Tokyo, we developed a seismic fuse, an EBF, eccentric braced frame, which effectively reduced the overturning forces to manageable size, to a manageable quantum. And that was the real breakthrough for us. What you see here is some of the time history, basically, which is the way that this structure would react over time with the input of an earthquake and the forces that generates. Having said that, we then extended our thinking. Well, what would happen if we've got Tokyo, we've got Seoul, we've got Mexico, each with their own specific geography, each with their own specific climate, each with their own specific infrastructure. Well, what would happen if we took some of our more famous jobs and moved them around the world? You'll be familiar with the Gherkin, you'll be familiar with Leadenhall. The BBVA Tower went to London, and we decided to shift to IFC, to Tierra del Fuego. Not bad. I'm not sure it would go too well there, it'd probably sink the place. And therein lies a story, because in moving the Gherkin, or Swiss Re, to Mexico, applying the earthquake forces, the pushing force at the bottom went from 4 units to 74 units. So the very thing that made Swiss Re such an elegant design for London, in many ways was totally useless in Mexico. So those of you who are architects here and are looking to develop buildings, it's really well worth visiting your local engineer and having a discussion on form before you really decide what to do. Sometimes you can reduce that 74 to about 10 at an absolute limit. There's absolutely no way with that current form that you will get from 74 to 4. And the great thing about Swiss Re is you get the wind for free. So once you've designed the building for its own weight, the overturning forces and forces in the system really are quite insignificant. And Dominic Monroe and others deserve great credit for the work that they've done there. Our next friend, so we packed our bags and we took Leadenhall and dropped that in Mexico also. And a slightly different story here. We got the pushing force at the bottom in London was 12 units. When we took it to Mexico, we got 13 units of force. It's not bad. That's not bad. Manageable. You could bring that down. But the really interesting thing was that the asymmetry of the form, where the mass and the stiffness, due to its triangular shape, change, it meant that the forces right at the top, or the stresses right at the top, were almost the same as at the bottom. And the reason for that is that it's vibrating in a different way. And it's the top that suffers as it sucks energy, the earthquake energy, out of the ground, and it effectively accelerates the top to a point where the forces at the top are about the same as they are at the bottom, or the stresses, I beg your pardon, the stresses are about the same. So, undefeated, we tested ourselves in our Mexico design and said, well, that was the effect on Gherkin. What really, if you compare like for like, would happen on the BBVA project? And what we found was that we got a base shear of 13, or a pushing force at the bottom of 13, a sliding force under earthquakes of 100. And again, that's not bad. I can do the math, about 8 times amplification. But the great thing was that because of the way that the building was conceived, when our earthquake came on the right, we see it, small push, we amplify through the jelly, through the soft ground, and we excite the structure above. What we were able to do was concentrate the failure into very discrete areas that over time could be replaced. And that really took the forces down to manageable sizes. We had to challenge the American code in doing this. We actually brought the draft of the American code forward to meet expectation. They were there. They were there when we applied the code as it stood. We would have had real problems. But along with our colleagues at SOM, Neville and Bill Baker, we formed a small party and challenged the code, and we brought the draft forward and actually used the draft to justify our design. However, the real interest here is that we took earthquake signals, real signals that were measured data, and using some software that Arup developed as part of crash technology, it's called Dyna, we were able to model in virtual time the effect of the earthquake. And what you actually see is quite significant, because you don't get this action. It's all based on the snaking effect or the vibration effect. Because of that, the force is reduced considerably. So I guess the message I'm giving here is that because of the high level of collaboration, the sharing of aims between the engineer and the architectural team, we were able to perfect a form that generated only 17,000 tons of steel above ground for in excess of 50 stories of building. But that really came about because of the open mind of the Rogers team to engineering ideas and to engineering philosophies, and working as one. Or as Mike Davis would say, you could never really figure out was the architect or the engineer. We were all a little bit of both. So, to really start to wrap up, we've related geography to appropriate technology, and we've said that there is a direct correlation. What we also go on to say is that in these new geographies, emerging economies, that this is going to take time to get right. And I would suggest to those investors in the room that moving to new geographies for tall buildings is really going to take about two construction cycles to get right, so that steel is there, so that HVA systems are there, energy codes are appropriately targeted. And once we've gone through that cycle, I think that the costs will, or the risk will diminish. What I'd like to do is just say that we went around the world and really set an agenda for those geographies that either are embracing tall buildings and or are expecting them to arrive in number. And I think that Asia certainly has a great responsibility to the rest of the world. They've built more tall buildings in the last 10 years than the rest of the world did in the last 50. So we would really look for leadership from the East. There is more experience there than anywhere. I really believe in our established centres that we have to maintain our infrastructure and refurbish more of our buildings. The key to this, to making a successful tall building, I believe, is to get the infrastructure right, because most of the energy or the carbon footprint is generated by people getting there over the life of the building. So our wonderful European cities, well, I guess the same applies. Don't be afraid of exploiting your transport hubs and creating more. That will give a relevance to clusters of tall buildings. And for that, I really believe that our government and our planning authorities have got to get their act together and support initiatives in a positive way. And finally, I think that the emerging economies haven't got long to get their planning right, but they need to. And that really means getting their regulations and their standards up to international standards. Getting adequate infrastructure so we don't have to build 2,800 car parking spaces under BBVA Bancomer. And really giving some stability to planning policy so that people can begin to invest with confidence. And if I really go back to the beginning and say, well, my initial analysis of where, what and how, I can see definitely South America, India and Asia developing. I think energy conservation and sustainability has to be the heart of what they do. They've got time to get that right. And to our designers, really find appropriate technology to suit those emerging economies. Thank you.
I thought the talk this morning was really, really fascinating. I think that the whole subject of tall buildings and how far mankind can go in terms of building structures of that kind. Having recently been to Dubai and seeing some of that most extraordinary tallest building in the world and wondering how on earth it can stand up, I think with Bob's talk, I've got a better idea today.
I thought it was very interesting. We're a very small firm, and the opportunity to discuss large buildings in our small office isn't often there. But it's very interesting to see the breadth and range of expertise which is applied within Arup, obviously, on such interesting buildings. It's fantastic. Bob was engaging and actually very exciting. I mean, the technologies being implemented are, very, very unique, and as such are interesting, and the possibilities from an architectural point of view are very, very exciting indeed.
I was particularly interested in the model where he demonstrates the snaking action of the seismic forces through the tower and how that withstands the structural integrity and the elasticity of the structure survives all that impact, and the sort of boffin-like modelling of the jelly mould, which of course beautifully illustrates the issue. Fascinating. As a layman, I'm not neither architect nor engineer, I found it absolutely riveting talk.
Very interesting. I think the shift from the traditional economies that produce towers to the southern hemisphere is fascinating. I hadn't really understood before what that meant in technical terms and how different the towers would be. And I guess that applies to all building typologies. So it was a great insight and very thought-provoking in that sense. I would welcome a further exploration into what that means in socio-economic terms for these economies, and whether following so directly a Western, sort of Northern European model of building is appropriate, and whether maybe it'd be more appropriate to develop their own way of doing dense urban development.